by measuring them. Some of these physics is full of constants. These are values or properties.
So this is going to go over the fine-tuning argument, and I'm going to list my own personal objections to them.
For which there's no theoretical basis. They're only determined by measuring them. Some of these constants are things like the charge of the electron, the gravitational constant, Planck's constant, and many others. If any of these numbers were different, our universe as we know it would not be the same. And we probably would not be here if that was the case. Why do these numbers have the values that they do? For that matter, why are we here? This is the core of the fine-tuning argument. It goes something like this. The constants of nature are statistically improbable. These constants are on a razor's edge, such that even a slight deviation would likely result in no life as we know it in the universe. Some take the argument further and say that this fine-tuning is so unlikely that it could not have occurred by pure chance, that there must be some agent that set up the constant.
Okay, first of all, that's an absurd statement, because anything can occur by pure chance.
To enable life. There are others that reject this argument for various reasons, but the discussion of fine-tuning is a very important
Even if something is incredibly improbable, it can still happen by pure chance.
Existential question. In this video, I'll take a look at both sides of the picture and give you what I think are compelling arguments both for and against the fine-tuning of the universe so that you can be well informed enough to make your own judgment, and that's coming up right now. Scale is gravity. The magnitude of the force of different forces. The most significant force on a cosmological scale is gravity. The magnitude of the force that one massive object has on another is determined by the gravitational constant. If this constant was too small, gravity would be too weak and planets wouldn't form because small objects may not be able to conglomerate to form bigger objects so easily. But if it was too big, the stars would burn up too fast, and there would not be enough time to form complex life. This is because stars and planets form as the gravitational force pulls its constituent particles together to form a celestial body. Stars exist in an equilibrium between the gravitational force which tries to collapse the star and pressure from the energy of fusion in the core which tends to counteract this force, preventing the star from collapsing. If gravity were stronger, the star would have to burn much more fuel to increase the counteracting pressure to avoid collapsing the star. This means the star would run out of fuel more quickly, and so the life of the star would be greatly shortened. The problem is that astrobiology experts say that it takes at least 1 billion years for life to form on a planet. And if the stars powering the solar system can't survive for that long, then its orbiting planets likely could not contain life. It's therefore very important to have the right strength of gravity. Just a 5% increase in the gravitational constant would result in at least a 1.2 billion year decrease in the lifespan of the Sun. More importantly, the Earth would orbit around 9 to 10% closer to the Sun.
Ouch.
This would lead to huge climate changes, and this in turn could probably mean the end of the human species. If we now consider the electromagnetic constant, the situation is similar. This electromagnetic force is responsible for the distance at which electrons orbit in atoms. It determines the size of the atom. If the force was weaker, the atomic size would increase because electrons would be further away from the nucleus. This could have an impact on chemistry as it would change the strength of chemical bonds. Since the electromagnetic force influences the atomic size, varying the constant of the force would also change the temperature of the stars. A higher constant would lead to cooler stars, and a lower constant would lead to hotter stars that would not last long, just like in the case of gravity. The reason for this is that if the constant is lower, then the Coulomb barrier would be smaller, making it much easier for fusion to occur. This would make the stars burn faster. If, on the other hand, the constant is sufficiently bigger, atoms larger than hydrogen could not form and stars may never ignite because the protons may not have been
I haven't even gone over my objections, I'm just playing this.
able to overcome the Coulomb barrier to fuse in the first place. Also related to the stability of atoms is the strong coupling constant. This is the constant related to the strength of the strong force which keeps neutrons and protons glued together in the nuclei of atoms. If it were lower, then again you wouldn't have stable, heavy atoms, as it would not be enough to overcome the proton-proton repulsion, similar to the situation with making the electromagnetic force larger. If the strong nuclear force was only 1% weaker, for example, atoms crucial for life, such as oxygen, carbon, and nitrogen, may not form in sufficient quantities inside stars, because the strong force would be too weak to keep the protons and neutrons bound together in the nucleus. If, on the other hand, the strong force was 2% stronger, no atoms might form, and we could be stuck with only hydrogen atoms. The reason for this is that the strong force would overpower the beta decay that is necessary for protons to be transmuted to neutrons. Neutrons are crucial to make the nucleus stable for larger atoms to form. If neutrons can't be formed, then all the heavier atoms beyond hydrogen and helium that we need for life may not form. Finally, if the value of the weak force constant was sufficiently bigger, then hydrogen would have turned into helium during the Big Bang in such large volumes that stars would either not exist or be much more rare. This is because, as I said earlier, helium forms from the fusion of 4 hydrogen nuclei, but 2 of these nuclei have to transmute to neutrons. This is enabled through a process called beta decay, which is due to the weak force. If this force was stronger, then it would enable this fusion process to occur in much more abundance, creating less hydrogen and more helium in the universe. This would not...
My objection is so incredibly obvious that it's astonishing that people that buy into this haven't thought of it.
Not only mean less hydrogen for stars to use as fuel, but also less hydrogen to make H2O. This means little to no water, and this means little to no chance for life as we know it to occur in the universe. If, on the other hand, the value was smaller, neutrons would not have changed into protons in significant numbers. This would leave us with a universe awash with neutrons and very few atoms in the universe. Free-floating neutrons would be stable, unlike the way they are in the current universe. But there are many other constants and parameters which represent other fundamental properties of the universe. And if you similarly change those, they would also have some significant effect on how our universe looks. So as you can see, the idea of fine-tuning does appear to be a compelling argument. Some say that these constants being so finely tuned in order to have the relatively stable, life-producing universe that we have could not have happened by chance.
Except this idea that it could not have happened by chance is absurd. Anything can happen by chance.
Is there another side to this coin? Just like everything in life, there are always 2 sides to every story. So, what are the counter-arguments? In general, while the universe appears to have constants that need to be within a very precise range, such that even slight variations could result in a different universe, it does not follow that this is unnatural. There would be no basis to make that judgment because unnatural would mean that other constants could or should exist naturally. That is not the case. There is no alternative existence in nature that we can conceive of in which nature would have different constants. And we've never measured any alternatives to these constants. We can't even say that it's improbable because probability indicates how likely an event is to occur. But this presumes that more than one event could occur. When it comes to this universe and the constants that it has, this may not be a valid presumption. We would need to assume that other universes with other constants were possible. We don't know whether that is the case. And if it was the case that other universes with other constants could occur, then there could have been or could be an infinitely many universes with all combinations of constants. In that scenario, it would be inevitable that a universe with our constants would be among them. Statistics can't be done with one sample. There are lots of things that could be statistically improbable or impossible, such as the chances of flipping a coin and getting heads 50 times in a row. This is about 1 in 1 quadrillion. I can calculate the probability of that because getting a heads or tails are both possible, and I know the probability of each. No probability based on statistics can be calculated for the different constants of nature. But these are philosophical arguments. Are there any scientific ones? One example which shows that precise fine-tuning may not be the case is the masses of the different fundamental particles. They're all measured, but the masses may not be independent, and some studies find that they must have certain values with respect to each other. Problems could arise, for example, with the stability of atoms if you change the quarks' masses. The same can be said for the electron. Although it's important that the down quark has a higher mass than the up quark to enable beta decay, which allows neutrons to transmute into protons and vice versa, the precise value of these quark masses appears somewhat arbitrary. They could have different values, but as long as the difference between them was about the same, not much seems to change. For example, the mass of the proton overall would not change much, since the quark masses only constitute about 1% of the total mass of the proton. The same applies to the neutron. It will have an effect on particle physics experiments such as that at the Large Hadron Collider, but in terms of macro-level effects on life, it may not make any difference. Another case against fine-tuning appears to be the mass of the neutrino. In the classic standard model, it was predicted to be massless, but we know now that it does have a very small mass because of measurements made on solar neutrinos. However, the exact mass of the neutrino seems to be arbitrary. The most important thing is just for the mass to be very close to zero. And the ratio of the masses of the three different neutrinos, electron, muon, and tau neutrinos, is important. But the precise number that the mass takes does not seem to make a difference. So the mass of the neutrino appears to be arbitrary, which is really the opposite of fine-tuning. The same thing applies for some other masses, such as the mass of the Higgs boson, which also appears to be somewhat arbitrary. Some fine-tuning arguments focus on the necessity of carbon, but carbon just happens to be very abundant, and it is a very versatile element because it can form bonds with other elements to make complex molecules. But biochemists suggest that life can be based on elements other than carbon too, such as silicon and germanium. It would be very different, but not impossible. Our anthropic bias may be constraining our imagination. I'm reminded of the story of the sentient puddle. This was told by science fiction writer Douglas Adams. A puddle wakes up one morning after a night of rain and says, "This is an interesting hole I find myself in. Fits me rather well. In fact, it fits me perfectly. It must have been made to have me in it." And as the sun rises and the water evaporates, the puddle keeps thinking that the hole was made to have him in it until he disappears. But there could be lots of holes with lots of sentient puddles with different dimensions of the hole. Similarly, if we change the constants analogous to the dimensions of the hole, it would be an alternate universe. But life as we know it then may be different. And would we continue to say in that alternate existence, this universe must have been made to have us in it? What is the definition of life? Could life be a Boltzmann brain, for example, a sentient information processor existing in space? Or is it any entity that uses energy, responds to change, and replicates itself? There could be many ways that life could exist, but our brains may be confined to think of life like ours being the only kind of life, and this universe made uniquely for that kind of life in it. If the universe was fine-tuned for life, why doesn't life play a central role in the universe? Why isn't it everywhere?
These are really good questions.
Why is most
asking, like, why would, yes, exactly, why is most of the universe hostile towards life if it was finely tuned? And this is completely true. I mean, if you look into it, if this astronaut right there in not the center, but a little bit away from, disoriented from the center of the screen, because I know it doesn't display my mouse pointer sometimes on these videos, but if this guy, we're not in a suit protecting him and everything as he's floating through space, the cosmic radiation would be doing intense damage to him, and even as it is, some of it's probably still getting through, but, he's got significant protection because he's in the spacesuit and everything, and, God forbid a solar flare went off at this point, that might very well not be enough. But so anyways, this is a very, very hostile environment. And, if you know anything, the journey to Mars, and everything, and the reduced gravity might not be, it might be a fundamentally one-way journey. You might not come back at all. Plus, Mars doesn't have a magnetosphere to shield, from the cosmic radiation. So, my cat is meowing at me. Anyways, what I was going to indicate. Hey you. cat thinks I'm talking to it. I wish I was on screen now, but that camera sucks. It really sucks. It's complete ass. Anyways, so, what I was going to say is, there's no magnetosphere to protect from the cosmic radiation. So, anybody that wants to go on there is going to have to immediately get underground as soon as possible to provide shielding and everything on that mission. And the fundamentally lower gravity constraints may run absolute havoc on a human body, which is why a lot of us are convinced at this point that we're not going to Mars in reality. I don't like being dumb and just buying into shit, so I've noticed the intelligence of skeptics, and I, as a result, have been learning from skeptics about shit like this. Anyways, let's keep going.
The universe hostile towards life. We could not exist, for example, in space or any other planet without life-saving technologies. Even if the universe is fine-tuned, it does not necessarily mean that there's an agent that created it. If an agent such as a god created life, presumably this agent would be outside the bounds of physics that he created in this universe. If that is the case, why must there be fine-tuning in the first place? This agent can do whatever the heck he wants. If he wants there to be life, he can create life in a totally chaotic universe. Why is he bound by fine-tuning? He could create life in a universe that had a lot of slop, where the constants could vary a lot. He could create life if the mass of the electron was as much as my house. The agent is not bounded by any of the laws of physics because he would have created those laws to begin with. So it may not follow that an agent exists, even if there is fine-tuning. The precise reasons why the masses are what they are and the constants are what they are is an open question, though. We can only speculate at this point, but one of the main things we should keep in mind is that our understanding of the universe is incomplete, and we know it's incomplete. We can't explain dark matter, dark energy, the asymmetry of matter versus antimatter,
we're still trying to even
and a
detect
host of other
it.
things. It's
We
quite
know it's
possible
there, but we've
that
never.
a future, more complete theory that may extend the standard model.
Dark energy in its present state is, essentially, at the state that we were in when we started to develop germ theory, and germ theory is really was more like a germ hypothesis at the time, way back then, in that, people started to speculate about the idea that life may exist on a fundamentally smaller scale than we were familiar with, and that they might they might god damn it, microbiology might exist, basically, and sorry, I've got a cat distracting me, but yeah, so they might exist on a level that we weren't used to, and then eventually microscopes, what? Misspeaking. Anyways, microscopes got built, and people were able to basically render visible the realm of microscopic life in a way that, we had not seen it previously and everything. But dark matter is in that state where it's been hypothesized, but nobody has been able to build a detector that is able to pick up on this, dark energy or dark mass. Like, it's just there.
And perhaps incorporate a quantum theory of gravity could not only answer these questions, but also explain.
Also, if we were able to detect it, it might, lead to some answers for some fundamental questions that are out there. But again, we're
in the theoretical bases for the constants being what they are. We saw a similar breakthrough with the electroweak theory, which united the weak force and electromagnetism. It showed that when we go to higher energies, two seemingly unrelated forces, electromagnetism and the weak force, unite, giving us a deeper understanding of the universe. There's a lot more physics for us to learn, and the future is probably going to be full of aha moments. Einstein said that nature shows us only the tail of the lion, but there's no doubt that the lion belongs with it. And we see the lion only as a louse sitting upon him would. It's possible we simply have not yet seen the lion that awaits at the end of the tail. And if you have a question, post it in the comments because I try to answer all of them. And if you like videos like this, then hit subscribe button. It costs you nothing.
Okay, so now that we're done, what are the potential other objections to the fine-tuning problem? Well, as we sit here and you're watching this video right now, all of the world's religions are at the same time observing the arguments that go into the fine-tuning argument. Every single one of them is drawing from the conclusion about the precision of these, variables that Brahma or Allah or whatever their god happens to be finely tuned it in the first place. Because the whole problem with the fine-tuning argument that so many of you Christians have not considered is that there is a fundamental difference between an intelligent designer and Yahweh himself, and everything. And what this means is, in effect, even if the problem with, the intelligent design taught in the schools and everything, is so fundamental in that regard, because all of these constants and everything, they may be able to suggest a very improbabilistic universe that was more than likely designed by some sort of intelligent designer, even though that is a bit assumptive at the end of the day. But if we were to grant these assumptions and we were to go over to say, okay, all of this stuff could not have happened by chance, and all of this amounts to, strong evidence for a potential designer. Well, the problem with that is that, designer is vague and nebulous. It's poorly defined. It's not, in essence, there's nothing to suggest that designer is necessarily the Christian God, or, the Buddhist, or it's not Buddha, or it's not, Allah or Brahman or Shiva or the big cat in the sky, or the flying spaghetti monster, etc., because any of these designers could have potentially done it. And so the big objection with the fine-tuning argument is that if we are to, the one that doesn't necessarily rely on science, even if we are to posit that there was an intelligent designer that was ultimately responsible for the universe, that doesn't mean that your personal or particular deity is the one that designed it. And so the problem with the fine-tuning argument is that it cannot help us eliminate potential gods and cross them off the list. It can't basically tell us which gods couldn't have created this universe. It can't do that. It can't eliminate options. It can't, narrow down the scope and say that, it definitely wasn't Brahman. It definitely wasn't, Zeus. It can't do that. So, and this is the fundamental problem with using the fine-tuning argument for, all of the theists, is that, literally it could be any theistic, God, period. That was the designer that was at the root of it all. And so this doesn't help any of them. And, with the world's religions in conflict with each other at this point, and, with all the religious conflict and sectarianism that's, going on around the world, this creates so many problems, because in order, science can't help us in this regard. It can't tell us, that, the Muslims are absolutely wrong about what they perceive as out there. It can't tell us the Christians are wrong. It can't tell us what any of the theistic, schools of thought are definitely wrong about what that designer happens to be and everything. And so that designer could, hypothetically be, the big cat in the sky shaping the universe with its cosmic meows. You just don't know. And, there is a fundamental distinction between positing a designer and your particular pet designer, the one that you love or is part that you pledge loyalty to, as a theist. You can't do that. You can't jump to that. So if the fine-tuning argument does suggest an intelligent designer, it doesn't necessarily suggest your particular intelligent designer.